Welcome to Visual Algebra Lecture 2.8, Semidihedral and Semiabelian groups. In the previous lecture, I constructed two families of groups, the dicyclic and diquaternion groups from the well-known quaternion group. In this lecture, I will construct two more families, the semidihedral and semiabelian groups, this time from the dihedral groups, using a process that I call rewiring. These groups were also featured in my 2024 American Mathematical Monthly article, Dihedralizing the Quaternions. Like the two from the previous lecture, these relatively unknown groups will be a rich source of examples for us going forward, and their Cayley graphs bring them to life in new and exciting ways. So let's dive right in. In the last lecture, we started with the quaternion group, whose Cayley graph is shown here. And using a dihedral group, really anyone, we just needed the reflection, we constructed the dicyclic and diquaternion groups. So please watch that lecture if you haven't already. But here's just a quick recap. So we constructed the dicyclic groups by replacing I, the generator, which is a fourth root of unity, with a larger nth root of unity. In this case, we get n equals, if we use n equals 8, we get the dicyclic group, dic 8, and since 8 is a power of 2, this is what we call a generalized quaternion group. And we can do this for any even n. It works for odd n too, but we don't get anything different. For the diquaternion groups, we start with Q8, and we throw in a reflection from the dihedral group, really any dihedral group. And to make that precise, we use the matrix representations of these groups. So I is represented by a fourfold rotation, which is zeta 4. Sorry, I'm really bad at writing zetas, so it looks more like a C. S is, so the matrix J is 0, negative 1, 1, 0. And then the reflection over here is just the complex reflection matrix 0, 1, 1, 0. So these three matrices generate the diquaternion group. And we can do this for not just for Q8, but for any generalized diquaternion group. Sorry, for any generalized quaternion group to get a generalized diquaternion group. Over here, or actually in both of these, I have highlighted the elements of Q8 as a subgroup. Over here, this is I and this is J. And so this is K, and the elements in the quaternion group are right here along the axes, whereas over here, this is the element for I. This is the element for J, so I times J is this element K, and you can see that the elements are no longer on the axes. They're, well, I guess these four are similar positions as these, though the elements are different. Actually, I guess the elements are the same. This is negative I. The difference is that this one being J means that this is J, negative J, K, and negative K, whereas this is I, J, negative J, K, and negative K, and negative I. At this point, I want to describe an alternate construction of the dicyclic groups, this time starting with a Cayley graph of the dihedral groups, because this is what will generate the construction in this lecture. We could have just removed the blue arcs from a Cayley graph of a dihedral group and investigated how can they be rewired. Let me show you what I mean with an example. Here's D8. It has a generator R of order 8 and a generator S of order 2. Suppose that we were to remove the blue arrows, leaving this so-called partial Cayley graph, and ask, how can we put back those blue arrows to get a different Cayley graph? And I'm still going to require that the generator is S. This is not the only way to do it, but one way is to say instead of S having order 2, it has order 4. And S squared equals R to the 4th, and then we get a 4 cycle like this, and we can continue in this manner. And this construction will lead to the dicyclic groups, and we can do this for any n that is even. So this is another way to describe what we did in the last lecture. It's another way to get to that final construction. Let me show you a different way to modify this graph. So if instead of deleting the blue edges, we delete the inner red cycle, then we get this partial diagram over here. And now I can say, how can we put back these inner red cycles? What I'm really asking is, how can we construct a group like this where R has order 8, or in general has order n, and there's an element S of order 2 that is not in the cyclic subgroup generated by R? Equivalently, what can we replace the relation SRS equals R to the n minus 1 with? So here we have SRS equals R to the n minus 1, or R inverse. So over here, if we do SRS, then which node here are we going to end up at? If n is the power of 2, then we can replace that relation with SRS equals R to the n over 2 minus 1. So one way to think about this is this red arrow, instead of wiring it backwards like this, we go halfway across minus 1 node. So here's what it looks like when we have n equals 8, and here's what it looks like when n equals 16. So halfway across minus 1 node. These groups are called semidihedral, and here's a formal definition. For each power of 2, the semidihedral group of order 2 to the n is generated by R and S, subject to R to the 2 to the n minus 1 equals 1. Think of R as this root of unity. There's a big red cycle taking up half the nodes. S squared equals 1. That means there's a blue edge right here. And then SRS equals R to the 2 to the n minus 2 minus 1. So blue, red, blue goes halfway across, minus 1. Now, this definition does not prove at all that this group actually has order 2 to the n. That actually has to be done separately, and I will not do that. But it does involve semi-direct products. I will mention kind of why it's true and how one would do it in a few lectures. But also, you can define this presentation for things that are not powers of 2, and you will get a group. You just won't get a nice family of group that has these properties. One more thing. Some books call this group the quasi-dihedral group. So QUASI dihedral. And they denote it QD. So in this case, it would be QD8 on the left. Sometimes they write QD16 because it has order 16. I don't like this for several reasons. One reason is because we just defined the diquaternion group, and I think having a DQ and a QD is confusing. But also because, as we will see later in this lecture, semidihedral to dihedral is analogous to semiabelian to abelian. So it's nice to have that connection. And also, this will be a semi-direct product as well. So there's multiple reasons why I like the name semi over quasi. Before I move on to the next slide, let me ask you a question. Do you see another way we can rewire these inner red arrows? Pause the lecture to think about this if you need to. And now I'm about to move on to the next slide, but let me direct your eyes to here. Look at these inner red arrows as I go to the next slide. Did you see what I did? I just reversed the inner red arrows. So instead of wiring the red arrow halfway across minus 1, I did halfway across plus 1. And that can be done by replacing the relation SRS equals R to the n over 2 minus 1 with R to the n over 2 plus 1. And that leads to a definition of a family of groups that I call semiabelian. So it's the same presentation, just we have a plus 1 here instead of a minus 1. The name semiabelian was suggested to me by a former undergraduate student who was taking my visual algebra class, Corey Andrews, in the fall of 2021. And it's just brilliant. Let me tell you why. So these groups are so uncommon that they don't really have a standard name. In some places, they are called the modular group because the subgroup lattice has a property that is modular. But I don't like that name at all for several reasons. First of all, every abelian group has a modular lattice, but also number theorists have an infinite group called the modular group that's closely related to modular forms, which is a big, important object in number theory. So calling this a modular group just is not great. Dublin and Foote calls this the maximal modular group because they're aware of that conflict. But it's not even clear what the name maximal refers to. I think I've seen this group called Ishikawa group somewhere else. The best name I've seen so far is the IMFDB. LMFDB. This is that database I told you about earlier. I encourage you to check it out. And they call it the other OD8 and OD16 for the other dihedral group. So there's the semidihedral group and the other dihedral group. But I really like the name Semiabelian because, as we'll see, this is to a certain abelian group the way that semidihedral is to the dihedral group. And just me saying that isn't convincing until I show you a couple pictures that should hit home exactly what I mean by that analogy. Let me ask you the same question that I finished the last slide with. Do you see another way that we can rewire these inner red arrows? Take a moment to think about that. Pause the lecture if you need to. And yes, there is one more way that we can rewire the dihedral group. Here it is. You've seen this before. It is an abelian group, C8 cross C2. And here's its Cayley graph, and here is its cycle graph. Notice that there is a maximal length 8 cycle consisting of the powers of R, but there's also another one generated by RS. So if you go red, blue, 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 you get this 8 cycle here, and they intersect at this 4 cycle like this. When this group has order 2 to the n, it has the same presentation as the dihedral, semidihedral, and semiabelian group, except for this last relation, which is SRS equals R to the first. So here SRS equals R to the first. Remarkably, this and the other 3 that we've seen are the only possibilities. So either SRS equals R to the minus 1, that's the dihedral group, or we go halfway across minus 1 to get the semidihedral group, or we go halfway across plus 1 to get the semiabelian group, or SRS equals R to the first to get an abelian group. Now to clarify, there are more possibilities for what exponent we can put here. But the point is that we will either get a smaller group or we will get one of these groups. So we don't get another group of order 2 to the n by replacing this exponent with something else. And that is in no way possible. But when we do see semi-direct products, I will say a word about why that actually is true. In other words, there are exactly 4 groups of order 2 to the n with both an element R of order 2 to the n minus 1. That's a big red R cycle that takes up half the elements. And then an element S that is not in that cyclic subgroup of order 2. So there's 4 ways to rewire that inner cycle of red edges. Let's compare the cycle graphs of the 3 non-abelian groups from this list. First of all, there's D8. We've seen this before. There's a red 8 cycle consisting of all their rotations. And then there are 8 reflections that each generate a maximal size 2 orbit. I've colored them so we can keep track of where the nodes go as we change up the groups. The semidihedral group also has this large red 8 cycle, and it has 4 elements of order 2, not 8. So these are the ones, if you think about the placement of the nodes, when there is a, they are right here in the inner ring. And then these 4 green nodes have order 4. The semiabelian group has 2 8 cycles. So it has this 8 cycle generated by R, because I think of it like rotations, but then just like the abelian group, it has another 8 cycle here. And what do you notice? You might notice that this is the same cycle graph as the abelian group, C8 cross C2. Let me write that down. So this C8 cross C2 has this very same cycle graph, which is one reason why I like the name semiabelian. The fact that these groups have the same cycle graph means that they have the same orbit structure. And this surprising fact has profound consequences that we will see when we study subgroups. I'll just tell you that those two groups actually have the same subgroup lattice, and that's the smallest example of two non-isomorphic groups that have the same subgroup structure. Now, I want to compare and contrast the matrix representations of the dihedral and semidihedral group. So Dn is generated by this complex rotation matrix and the complex reflection matrix, but Sdn, the semidihedral, is very similar. You just put a negative sign in front of this 2,2 entry. Now, let's compare and contrast those of the abelian and semiabelian group. So the abelian group we can represent with this matrix. That's the same as the rotation matrix. It just doesn't have a bar here. So this is a scalar of the identity matrix, so it commutes with everything. So this is an abelian group. And the semiabelian group can be achieved by putting a negative sign in front of this 2,2 entry to get this. And a mnemonic is that semi means halfway around the unit circle, which is zeta to the n over 2, or just -1. So dihedral, semidihedral, they differ by going halfway around the unit circle. Same with abelian and semiabelian. You see why I love that name? It should be noted that the semidihedral and semiabelian groups only exist when n equals 2 to the m. And in this case, we also have a generalized quaternion group or a dicyclic group that's represented with the same rotation matrix here. And, well, no longer the reflection matrix, but you put a negative sign in front of either of these entries, and you get the matrix for J, which has order 4. Now, I said above that these groups only exist when n is a power of 2, but that is only partially correct. We can define these groups of matrices for any n. In other words, they always generate some group, but it's not clear what those groups are. It's only when n is a power of 2 do we get this nice group of order 2 to the n that has this predictable structure. So it's a fun exploratory question to ask, what happens if we take this group here and let n equals 3? Or what if we let n be 10 or 5? And these are things you can explore with programs like Matrix Calc, which is a great website where you can quickly multiply matrices together that include complex numbers. You can use programs like GAP, and I assign this as homework. I think the first time I taught this, I did not know what SD3 was, and so I put it on the homework and had students figure it out. And same thing with like SA3. I think one of them ended up being dicyclic, another one ended up being the special linear group of order 24 over Z3. But I don't know what the general pattern is. If there is a pattern for certain families of n, like even n or odd n, or things that are like 1 mod 4, that is a wide open exploratory question, which is, would make a great undergraduate research project and probably publication in like an undergraduate journal. And there's so many other questions you could ask, like what happens if you throw in the matrix for J into one of these presentations? Or what happens if you put a negative sign in front of here? You use one of these 3 matrices in the dicyclic group presentation. I don't know the answer to these, and there's so many questions like this that would be fun to explore. So I encourage you to do it, and if you have answers, let me know in the comments. Let me summarize one of the main ideas of this lecture that we'll understand better when we study semi-direct products of groups. This is the theorem. There are exactly 4 non-abelian groups of order 2 to the n that have an element R of order 2 to the n minus 1. That is a big red R cycle that takes up half of the elements. There's the dihedral group that we started with in this lecture. There's the dicyclic group that we constructed in the previous lecture. And this one actually has an element S of order 4. And then there are the semidihedral and semiabelian groups that we constructed in this lecture. Now here's a picture. It's not these 4 groups. It's the dihedral over here, and semidihedral and semiabelian, and then here is an abelian group with that property. And I'm putting these 4 together to show you how they are related. So remember I said that you can think of semi as being halfway across this unit circle, which is r to the 2 to the n minus 1, or just negative 1. So here's the abelian group, where this inner node is connected to the one right next to it. And the semiabelian group, this one is connected to not the one next to it, but halfway across from that. So these 2 red arrows differ by 180 degrees. Then there's the dihedral group, which this node is connected to the one before it. And if you go 180 degrees across there and connect those up, you get the semidihedral. So there's abelian is to semiabelian, i.e. 180 degrees, what semidihedral is to dihedral. And we saw this not only in the Cayley graphs, but also in the presentations and also in the matrix representations. So I love how those 3 viewpoints of these groups all tie together, especially with the word semi. And as we'll see, there will be 4 semi-direct products of this group C to the 2n minus 1 with C2, and those are these 4 right here, which is more evidence that the word semi is the correct word for these groups. As before, we can ask, what groups do these presentations describe when 2n, or equivalently n, is not a power of 2? I wrote 2n because here you have 16 everywhere. The groups have order 2 times 16, 32. So you can define these presentations just like you can define those matrix representations for general n. And I don't mean general n, I mean replace this power of 2 with just a non-power of 2 and say, what groups do you get? That's a fun, unexplored project. At the end of the last lecture, after showing you the diquaternion groups, I showed you several Cayley graphs that look like the diquaternion group, but were not. And I left it as an open-ended puzzle. I said, what groups are these? And I'm going to do the same thing here. So here are 2 graphs that look like Cayley graphs of groups. And I want to ask you, are they Cayley graphs of groups? And if so, what groups are they? Now, these define presentations. You can write out something like this is generated by R and S, where R to the 8 equals 1, and S to the 1, 2, 3, 4, 5, 6, 7, and S to the 8 equals 1, and then you can write down like red, blue equals blue, red. Okay, so this one is abelian, RS equals SR, and you can, it's not entirely clear that there isn't any other relation in here. I think this is it. And this one here is the same thing. It's just these inner red arrows go the opposite direction. So these define groups. So over here, you'd have the same presentation, but you would have S or RS equals SR inverse. So you'd have RS equals SR inverse. So these define groups. The question is, do they define groups of order, in this case, 16? Or do they define smaller groups like we saw with that Peterson graph example? Now, since these Cayley graphs have an element of order 8, there are only 6 possibilities. Wait, where did 6 come from? So there were the 4 semi-direct products that I have, the 4 rewirings of the dihedral group. But the cyclic group C16 also has an element of order 8, right? You take a generator and square it, that element has order 8. And then there's the generalized quaternion group. So this one, if it is a group, it is abelian. There's red, blue equals blue, red. So it's going to have to be one of these 2. And it should be pretty quick to figure out which one it is. is there an element of order 16? I suspect there's probably not, in which case it's probably this one. This one here, well, there is an element. So let's see, red is an element of order 8. Blue also has order 8. So that's going to eliminate, and red inverse has order 8. So that's going to eliminate right away D8. And I'll let you think about which of these it might be, if it's any of those. And you can answer this pretty quickly by typing these presentations into a program like GAP. GAP is a computer program that'll quickly tell you what groups certain presentations are and other statistics of groups. Or maybe you could just do this by hand, or by going to the LMFDB and looking up groups of order 16 that have C8 as a subgroup. Now, one thing that I tell my students to do if I give them a puzzle like this is write the order of every element if it actually is a group. So this would have order 1, this would have order 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. This one has order 4. This one has order 8, and so forth. And that will tell you, that will narrow down what the list of groups can be. Here's another few examples. So this time I did not put an abelian one in here because the inner red cycles go in the opposite direction, but I wired the blue edges up here to a quarter of the way across -1. And then here I did it, I guess, just over by 2. So you could ask similar questions about these. Are these described presentations of groups? What groups are they? Are they actually groups of order 32, or are they somewhat smaller, like the Peterson graph example? And if they are groups of order 32, what are they? So you can answer this with GAP. You might be able to play around with this. You can modify these in other ways. You can put this inner red cycle the opposite direction. You could modify this inner red cycle like we did with the semidihedral or semiabelian. You could, you could wire the red arrow to be one halfway across and one less, like this, or you could connect this blue edge from, instead of a quarter of the way -1, what about a quarter of the way +1? So or you could make these blue edges double-sided, so have order 2, which really isn't much different than just twisting this, I think, by a little bit. So there's a whole bunch of possibilities that are worth exploring. It should be fun. As before, if these are groups, there's only a short list of order 32. There's a short list of what they could be. So both of these have an element of order 16, this big red cycle. So there are only 6 possibilities, and both of them, red-blue is not equal to blue-red. So that gets rid of the abelian groups. And so if these are groups of order 32, they have to be one of the following 4. And my question is, which one are they? Now, these inner elements do not have order 2 because look at it, blue, blue. So if this were dihedral, these would all have to have order 2, so we can eliminate that one. So which of the remaining ones, if any, are these groups? And how can you tweak these even further and answer that same question? Okay, so those are some fun things to explore. Here's one more. Are these Cayley graphs of groups? And if so, what groups are they? So now I'm rewiring, instead of going halfway across minus or plus 1, I'm going a quarter of the way across -1. And here I'm going a quarter of the way across +1. Since there's an element of order 16, once again, there are only 6 possibilities. These are not abelian, so they have to be one of these. And these inner elements do not have order 2. So, I mean, if you go blue, red, so that means that they can't be D16. So if they are groups, they are one of these 3. But I don't actually know the answer. I have not taken the time to explore this. You could write down the presentation RS, where R to the 16 and S squared equals 1. And then you could write, what is it, SRS. So you could write SR. This is really just a R cubed. This is really just a Cayley graph version of the question that I posed earlier with changing their presentations. My guess, just intuition, is that this is going to be a smaller group. This is like that Peterson graph example. I could be totally wrong. It might be one of these two. I suspect that well, it also can't be Q32 because the generalized quaternion groups don't have only have one element of order 2. Remember, that's -1. All of those inner elements have order 4. So right here we see S has order 2 and R to the 8 has order 2 if those are actually distinct elements. So that will get rid of this. So these groups, if they represent groups, have to be one of these two. That is, if they are groups of order 32, but they also might represent something smaller. So I encourage you to go into GAP and plug in these presentations and check it out and see what you get. I kind of like not knowing, but I also would like seeing the answer in the comments, knowing that some of my listeners are into this and like to explore it. Okay, so that is a good place to stop. In the next lecture, I will talk about semi-direct products. I will not do this formally because we don't have the tools. We need to talk about normal subgroups and homomorphisms, but a semi-direct product in terms of Cayley graphs can be thought of a way to rewire certain edges. And that's what was one of the themes of this lecture, is rewiring these inner red edges. So it's natural to talk about that more general construction and how to do this in terms of Cayley graphs, and it will give us a lot of intuition as to what not only semi-direct products are, but what operations that are called automorphisms are, which are rewirings of the Cayley graphs. And that will give us intuition as we go into topics like normal subgroups and homomorphisms in chapter 3 and 4, respectively. So I think I'm going to leave it there. See you next time.